All right, welcome back, everyone. We're diving headfirst into another fascinating paper today.
Yep, super interesting one.
It's Why Do LLMs Attend to the First Token? Barbero and colleagues. So I guess for those who are just tuning in for the short version, here's the kind of TL. This paper tackles this kind of weird phenomenon where LLMs, they pay a lot of attention to that very first token, right? Which, a lot of times is just that BOS token, beginning of sequence, right? Doesn't really have any meaning per se.
Right, like a placeholder almost.
Yeah. So what the paper finds, and they kind of back this up with both theory and experiments, is that this actually isn't just some random quirk, right? It's not just like noise. It's actually a really important mechanism that the model learns.
Like a strategy almost.
Yeah, like a strategy. And it's a strategy to avoid what they call overmixing.
Ooh, overmixing, yeah.
So basically, if you have too much information mixing between the tokens in your sequence, that can lead to all sorts of problems, like, for example, rank collapse.
Yeah, where they all kind of get mashed together.
Yeah, you get these representational collapses. The model just can't distinguish between different pieces of information anymore.
Right, like it loses track of what's what.
Yeah, exactly. So this attention sink, focusing on that first token, it acts as a way to kind of control the flow of information and make sure that the model doesn't get overloaded.
Kind of like a pressure valve, right?
Exactly, like a pressure valve. So we'll be digging deeper into that, how they arrived at this conclusion. We'll talk about their experiments with models like Gemma and Lama.
Yep, some big names there.
Yeah, really, really interesting stuff. And of course, we'll talk about why that BOS token is so surprisingly crucial.
It's not as simple as it looks, is it?
Nope, not at all. All right, so for the rest of us who are in it for the long haul, let's really unpack this attention sink business. When we talk about these attention sinks, what exactly are we talking about?
So picture this, okay? Imagine a network, right? A bustling network where information's constantly flowing between different nodes.
Okay, got it. A network, lots of information buzzing around.
Right, and in a transformer model, these nodes are basically the tokens in your input sequence.
Okay, the individual words or pieces of the text.
Exactly. And how this information flows, well, that's all governed by the attention mechanism.
Attention, yeah, that's like how the model decides what to focus on, right?
Exactly. Now, an attention sink, think of it like a central drain in this network.
Okay, a drain.
Yeah, it's a specific token that's just pulling in a huge amount of the information flow from all over the network, specifically from the attention heads.
So one specific token is attracting a lot of attention.
A disproportionate amount, yeah. And what's really weird is this often happens with the first token in the sequence.
Like that BOS token, the beginning of sequence marking.
Yeah, that's the one. It's like, why would a token that doesn't really mean anything, semantically speaking, be such a magnet for attention?
Yeah, that's super weird. You'd think the model would be focusing on the words that actually have meaning. The verbs, the nouns, the juicy stuff.
Right. You'd think so. And that's what makes this paper so fascinating.
So before this paper, what did people think was going on with these attention sinks? Were there any theories?
Oh, yeah. People definitely noticed them. They've been linked to a bunch of different things, like easier quantization of these massive models.
Quantization, so that's like compressing them to use less memory.
Yeah. Exactly. Makes them a bit more manageable. And then there's improving the efficiency of KV caching.
KV caching, that's a technique for making text generation faster, right?
Much faster, yeah. Then you've got streaming attention mechanisms for dealing with really long sequences.
Okay, yeah, those are super important for handling like huge chunks of text.
Huge chunks, exactly. But then there's also the less fun stuff. Attention sinks have even been linked to some security vulnerabilities.
Oh, wow. Okay, so they're not all sunshine and roses then.
Not exactly, but the key difference with this paper, the thing that really sets it apart, is the perspective shift.
A perspective shift.
They're not just looking at the consequences of attention sinks. They're asking why. Why do LLMs develop this behavior in the first place?
Okay, so they're trying to get to the root cause. Instead of just saying, oh, this is happening, let's try to fix it, they're asking, why is this happening at all?
Exactly. And their core idea is that these sinks aren't just a side effect. They're a learned mechanism. They serve a purpose.
They're intentional.
Yeah.
The model is doing this on purpose.
That's the hypothesis, yeah.
And it's wild, right? Like the paper mentions, in a model like Llama 405B, almost 80% of the attention can go to that initial BOS token.
80%. That's crazy.
It's a huge amount of attention focused on something that seems totally empty.
It's like, is it just staring at a blank wall?
Yeah, you got to wonder what it's doing. But the paper argues that it's not just random. It's all about how transformers process information.
Right. Remember how we were talking about that information flow? Well, the attention mechanism is the main way that information gets mixed between tokens in the sequence.
Okay, yeah, I'm following. So you got all these tokens, and they're influencing each other through the attention mechanism.
Right. But here's the thing. If this mixing happens too much, too aggressively, it can cause all sorts of problems.
It's like adding too much salt to a recipe. It can ruin the whole dish.
Perfect analogy. And one of the big problems is this thing called rank collapse.
Rank collapse. Okay.
So you have these vectors, right, representing different words, and if you keep applying transformations that push these vectors closer and closer together, well, they lose their distinctiveness.
It's like blending all the colors together. You end up with just a muddy brown.
Yeah, exactly. And that's rank collapse. The vectors get stuck in a low-dimensional space. They become too similar.
So the model can't tell the difference between different words or concepts anymore because their internal representations have become too similar.
That's exactly it.
Frick.
And then there's representational collapse, which is a big problem with long sequences. The transformer might get so fixated on the early parts of the sequence that it forgets about the later parts.
Oh, I see. So it's like the beginning of a story overshadowing the ending.
Exactly. And they also talk about over-smoothing in graph neural networks. It's the same kind of idea. You mix information too much and everything starts to look the same.
Right. So all these different collapse scenarios, they all come down to this idea of uncontrolled information mixing being a bad thing. So how does this attention sink, focusing on that first token, help prevent that? How does it stop this overmixing from happening?
Well, think of it like this. That first token, that attention sink, it acts as a sort of regulator. It draws a lot of attention, especially in the early layers of the model.
Okay, so it's like a sponge, soaking up some of that initial attention.
Yeah, and by doing that, it slows down the rate at which information mixes between the other tokens.
It controls the flow, right? Prevents things from getting too chaotic too quickly.
Exactly. It's like a pressure valve, releasing some of that pressure. And by regulating the mixing, it prevents those collapse scenarios we talked about.
Clever. So it's not just that the first token is receiving a lot of attention. It's that by receiving that attention, it's actually protecting the rest of the sequence from being overwhelmed.
Yeah, it's like a bodyguard for information.
I love that.
Yeah.
A bodyguard for information. And they even formalize this idea, right, with a proposition.
Yeah, proposition 3.1 in the paper. It shows that rank collapse actually implies representational collapse, although the reverse isn't always true. It highlights that these are related but distinct issues, and the attention sink helps with both.
Okay, that's interesting. So rank collapse is like a specific kind of representational collapse.
Yeah.
But there can be other ways to have representational collapse, and the attention sink helps to prevent all of them.
Right. And to really understand how it does that, they use this mathematical tool called the Jacobian Norm.
Ooh, getting into math now.
Just a little bit. Think of the Jacobian norm as a way to measure how sensitive the output of a function is to changes in its input.
Sensitivity. Okay, so like if you change the input just a tiny bit, how much does the output change?
Yeah, exactly. And in this case, they're looking at how much a change in one token's embedding affects the embeddings of other tokens later on in the network.
So it's like measuring the butterfly effect within the LLM. One tiny change can ripple through the whole system.
That's a great way to put it. And they have this theorem, Theorem 3.2, which gives a more detailed boundary on this over-squashing effect.
Over-squashing, that's when information gets lost because of too much mixing, right?
Right. And the theorem shows that this sensitivity is affected by a bunch of things. The depth of the network, the number of attention heads, the length of the input sequence.
So the deeper the network, the more heads, the longer the sequence, the more sensitive it becomes to these small changes.
Exactly. And the theorem also highlights the role of these weighted paths across attention heads. They can amplify or dampen these sensitivities.
Interesting. So it's not just a simple equation. There's a lot of interplay between different parts of the model.
It's a complex system for sure. But the point is, the attention sink helps to manage this complexity. It limits the ways in which these small changes can propagate and cause problems.
It's like a shock absorber for the network.
Yeah, I like that. And they even have this figure 1, that shows how the sink token absorbs some of this perturbation energy, making the token embeddings more stable.
Makes sense. If a tiny change happens early on, the sink helps to contain it and prevent it from messing everything up downstream.
Exactly. And based on this, they made a prediction. Larger models and models trained on longer sequences should have stronger attention sinks.
Because they would be more prone to this overmixing, right? More layers, more information flowing around.
Precisely. And they tested this prediction with experiments on Gemma 7b.
Okay, tell me about those experiments. What did they do?
One of the key analyses was a perturbation analysis. They would take a sequence, change one token, and then see how the representations of the other tokens changed.
Okay, so they introduce a small change and then observe how it spreads through the network.
Right. And they did this with and without the BOS token.
So they wanted to see how the presence or absence of that attention sink affected things.
Exactly. And what they found was pretty striking. When they removed the BOS token, that single token change had a much bigger impact on the other token representations.
So removing the attention sink made the model more sensitive to those small changes.
Much more sensitive, yeah. And they have this figure 2, that shows this really clearly.
I'll have to check that out. And what about the attention maps? Did they change when the BOS token was removed?
Yeah, they did. In figure 3, they show that removing the BOS token made the attention maps smoother.
Smoother, so that means the attention was more evenly distributed.
Right, and that smoothness actually correlates with higher values of the Jacobian norm.
So it's more evidence that the BOS token is actively working to prevent this excessive mixing.
Exactly. And they didn't just look at the overall attention patterns, they also looked at individual attention heads within Gemma 7b.
Okay, so zooming in even further, what did they find at the individual head level?
Well, they found this one head that was super interesting. It seemed to have 2 distinct modes of operation.
2 modes, like a switch.
Yeah, almost. In figure 4a, you can see that this head would activate really strongly when it saw an apostrophe in the preceding context.
So if there was an apostrophe, this head would pay attention to that specific location.
Yep, but if there wasn't an apostrophe, its attention would default to the BOS token.
So it's like you learn this rule. If I see an apostrophe, focus there. Otherwise, default to the beginning. That's super specific.
It is. And when they looked at the norms of the value vectors for these different tokens, figure 4b, they found something really interesting. The BOS token had a much lower norm compared to the apostrophe.
Lower norm, so that means its value vector was closer to 0.
Right. And what that means is that when the head attends to the BOS token, it's basically outputting a low magnitude vector. So it doesn't really change the embedding of the current token that much.
It's like a do-nothing instruction.
Yeah, almost like a standby mode. And they connected this to the Bigram back copy task.
Oh yeah, what was that about?
It's a theoretical task where a model has to copy a previously seen token. And the kind of attention head they found, one that can be selectively activated based on context, seems like a real-world mechanism for doing that.
Makes sense. So these low-level attention patterns can actually contribute to higher-level cognitive abilities. That's amazing.
It is. And remember that prediction they made about larger models and longer contexts having stronger attention sinks?
Yeah, did they test that out?
They did. They pre-trained smaller models on data sets with different maximum context lengths.
What happened?
Well, as you can see in figure 5, the models trained on longer contexts ended up with much stronger attention sinks.
So the prediction held up, longer contexts, stronger sinks.
Yep. And figure 5b shows that the rate at which these sinks developed also increased with the context length.
Interesting. So as the models see more and more data, they adapt and develop these sinks to handle the increased information flow.
And importantly, these models, even with different sink strength, achieved similar performance. That suggests that the sinks are necessary for learning effectively with longer contexts.
So it's not just a random byproduct, it's an intentional adaptation.
That's the idea.
Cool. So what about the really big models, like Llama? Did they show the same pattern?
They did. They looked at Llama 3.1 models of different sizes, 8B, 70B, and 405B.
Wow, 405 billion parameters? That's a monster.
It is. And in Table 1 and Figure 6, they show how the sink metric, a measure of sink strength, varies across these different models.
And what did they find?
Well, the smaller 8B model actually seemed to be more active with weaker sinks overall. But as the models got bigger, the sinks got stronger.
That's the same trend. Larger models, stronger sinks.
Yep, just like they predicted.
Awesome. Now, the paper also tackles a really interesting question. Is it the BOS token itself that's special, or is it just the fact that it's always at the beginning?
Right, good question. So they did a bunch of pre-training experiments with different ways of handling the BOS and EOS tokens.
So they played around with where those tokens appear in the sequence.
Yeah, and they used different attention masking schemes too. They compared the standard causal masking with intra-document masking.
Interesting. So they were really trying to isolate the effects of the BOS token itself.
Exactly. And their results are in Table 2 and Figure 8. What they found is that if a model is consistently trained with BOS at the beginning, it definitely relies on it for the attention sink.
Okay, that makes sense. It learns to use what it's given.
Here's the cool part. Even if BOS isn't always at the beginning, or even if it's not there at all, a sink still forms at the first token.
So it's not about the BOS token specifically, it's about the first position.
That seems to be the key factor. And if you force BOS to always be at the beginning during training, the sink gets even stronger.
So it's like the model is really good at adapting to whatever it's given, but it prefers to have a consistent starting point.
Exactly. It needs that anchor to manage the information flow.
Awesome. And they also did some further analysis in Appendix B to show how the BOS token actually helps prevent overmixing, right?
Yeah, they looked at token similarity and representational distance. Figure 9 shows that including BOS leads to more diverse token representations as the prompt gets longer.
So it's preventing those representations from collapsing into each other.
Exactly. And Figure 10 shows that BOS has a really low norm for its value vector.
So attending to it doesn't really change anything. It's like a neutral operation.
Right, like a do-nothing instruction. And that's how it helps to prevent overmixing.
So basically these attention sinks, especially the one at the beginning, aren't just random quirks. They're a crucial mechanism that LLMs learn to control information flow and prevent problems like rank collapse and representational collapse.
Exactly. They're like a safety feature built into the model.
And understanding this is super important as we build bigger and more complex models, especially if we want to use them for things like long-form text generation.
Absolutely. It gives us a deeper understanding of how these models work and how to make them more robust and reliable.
This is super cool stuff. It really makes you think about the future of LLMs. Like, could we design even better mechanisms to prevent overmixing, maybe without relying so heavily on that first token?
Yeah, that's a great question. And what are the implications for things like context window length? Can we overcome those limitations if we have better control over information flow?
Lots of exciting avenues for future research.
Definitely. And for anyone who wants to dive deeper into the math and the experiments, definitely check out the full paper. It's worth the read.
All right, that's our deep dive into attention sinks for today. Thanks for listening.
See you next time.